as Caleb mentioned, we're kind of at a turning point now. We've already seen how just by looking around at the world we live in today, we can deduce how evolution happens and how variation can be selected for. And Caleb has shown us how that variation comes to be, what the actual driving mechanism for that is. But as they both alluded to earlier, there's kind of a piece of the puzzle that is missing. And that comes from the fact that something like 99% of everything that's ever lived on our planet is extinct. And so there's a huge treasure trove of life that we don't get to see and experience. And if we really want to understand evolution and the place of everything on Earth, we have a lot of gaps in the family tree that we need to fill. And so to do that, to fill those gaps, we look at the fossil record. Now the fossil record, as you can see here, a lot of it is bones, but it's also things like shells and footprints and burrows, and even sometimes some softer, squishier bits get left behind for us to find as well. It's everything that ever lived left behind for us to find. And by looking at the fossil record, we can kind of go back through the story of life on Earth. We can turn back these pages and understand how everything is connected. And I hope to show you, we can also see some processes that we wouldn't otherwise really think were going on. So the fossil record lets us look through this book. It itself is kind of like a photo album. It presents us a series of snapshots of different moments across Earth history that we can then look at and deduce what's going on. So just like you might look at a family photo album and say, there's grandma and grandpa, and there's mom when she was a kid, and that's when mom and dad met, and there's me as a baby. These aren't a full movie of your entire life, but they're key snapshots of moments that you can stitch together and put together the story of what's going on. And the fossil record is the same thing. There's one caveat. The fossil record is not perfect, and it's not complete. Some of the photos are missing. They've been torn in half. Some of them are stained, and we have to work really hard to figure out what's going on. And so I'd love to tell you about how bats evolved and continue talking about that cute little fruit bat that Caleb showed you, but I can't really do that because bats don't have a very good fossil record. So this is Microraptor here. This is a little bat from, I believe, Wyoming. I could be mistaken. And it's something like 45, 50 million years old, and it already looks exactly like a bat. It's already got this long arm and these long fingers that you can just imagine webbing being stretched between to make a wing. Now, if we really wanted to understand where these features came from and how bats fit in with everything else, what we'd want to find is a fossil of a bat that has shorter fingers and shorter arms, something that is recognizably related but still different. And for now, at least, we don't have that. I expect, as all paleontologists do with hope, that eventually those missing bats will be found. But for now, we don't have them. So instead, I'll talk to you about the other major group of flying animals, the birds, which is a very different story for. So birds are a ubiquitous part of our world. If you look outside on any given day, you're very likely to see a bird or two doing their thing. And they're a beautiful group of animals that do a lot of different jobs in their environment. And they're kind of all recognizably related. All birds have feathers and beaks and wings, and some fly, some don't, but they all do their thing. And they're incredibly diverse. Birds we like to think of our world as being run by mammals. We're kind of the ones in charge. But not really. We have about 4,000 species of mammals compared to something closer to 10,000 species of birds alive today. So birds are pretty much the most diverse group of things with 4 limbs. They're kind of neck and neck with lizards, so we'll see who wins out. I hope lizards do, personally, but that's besides the point. But birds we're fortunate with because they have a great fossil record. Because if we wanted to see where birds come from, what they're doing, in the modern world, we'd be out of luck. Birds' closest living relatives are crocodiles like this here. And you can tell that from some quirks of their anatomy and by looking at their genes, that these two are pretty close cousins. And in our world today, that's all we have. And if you wanted to look at how birds become birds and how all their birdy things came to be, this is a pretty bad place to start. There's not much similarity there. But unlike bats, birds have a great fossil record. You've undoubtedly seen fossils of bird relatives in any museum you've been to today, or in the past, if you haven't been to a museum today. And people love these animals. They're well-studied, richly sampled, there's a ton of them. And it's because birds are dinosaurs. And we've really come to understand that better in the last couple of decades. But birds are dinosaurs. And if you want to see a dinosaur, you can look outside and see a beautiful owl or the humble pigeon. And these are simply the dinosaurs that, when the end of the Cretaceous came around and that asteroid slammed into Mexico, they shrugged up and said, no big deal, let's just keep chugging along. And they're still here with us today. And so by looking at dinosaurs and their fossil record, we can start to see how birds became the animals that they are today and where they fit in with the rest of the tree of life. So let's turn to a bird and consider some of the features that we might be interested in looking at. And I'm going to talk about 4 today, the most obvious being feathers. No other animal alive today has feathers but birds. If you find a feather on the ground, you can say a bird has been here. And wings. Birds, like bats, have wings. They're very unique to birds. They're a special kind of wing. And any bird you see, barring a few that might hide it in their feathers, you can see their wings. Birds also have a tail fan that they use kind of as a rudder when they're flying to control their speed, their direction, things like that. And most other animals today have either kind of long tails or, like us, no tail at all. So birds are kind of unique in this way. And then the last thing we'll talk about are air sacs, which if you haven't heard of, I don't blame you. They're kind of weird. Suffice it to say for now, they're just a special adaptation of birds' lungs that make them very light and very good at flying. So if we wanted to look at these features and where they came from, we might start by thinking, well, let's look for animals that are flying, because all of these various features of a bird seem perfectly suited for an animal that's trying to fly. But if you did that, you'd start to come up short. And that's because of something that the fossil record shows us. And it's a process that's called exaptation. It's one of the ways that evolution works that we wouldn't really be able to see if we were just looking at the world around us today. And so exaptation was coined by Elizabeth Verba and Stephen Jay Gould, 2 brilliant minds in the field of paleontology and studying evolution. And all it really is a shift in the function of a trait over its evolution. It's something that has appeared initially to serve one purpose, to do one job, and that has then been co-opted into doing something else. A great example of something like this is actually bubble wrap. So bubble wrap, if you weren't aware, was initially conceived of as a textured wallpaper that you could put up and impress your friends, I guess. But nobody wanted that. I don't want bubble wrap as a wallpaper. I'm very clumsy, and if I were to fall into my wall and it would pop, that would not make me happy. And it didn't make many people happy otherwise. So bubble wrap's kind of out of luck. They made it as a wallpaper and nobody wants it. But they found out that it had a great purpose, a great other thing it could do as a packaging material. And so they co-opted it to do this. They shifted its function to do a different job. And bubble wrap is still around with us today whenever you get something from Amazon delivered to your house. And the same thing can be seen with the various features of a lot of animals, and hopefully I can convince you at least that it's the same thing happening with birds. So let's start with feathers, the most birdy of bird features, if you will. Nothing, like I said, on Earth today has feathers except birds. And when you think of a bird feather, you probably think of something like you see on the wing here. It's long, it's got a quill, maybe if you were a wizard you'd use it to write on parchment. But when feathers first appear in the fossil record, they're not like this. So this is an animal called Sinosauropteryx. And all this little black fuzz running along the back of it, those are feathers. They're not quite what we think of today in terms of feathers. They're more like hair. They're simple little filaments that cover the body. And this is what looks to be the ancestral form of feathers. This is what they're like when they first appeared on these animals. And this isn't the most fair example of them trying to convince you that they're doing something different, because Sinosauropteryx is very closely related to birds. It looks a lot like a bird in a lot of ways, and it's on that line of dinosaurs. But we see the same thing in other dinosaurs too. So this is Culindrodromeus, and this is an artist's representation of what it may have looked like in life. And we see these same little hairy feathers sticking out across various parts of its body. But this is not related to birds. You might not see it doesn't really look it, but its closest relatives are things like Triceratops and Stegosaurus, things that in a million years no one would confuse for a bird. So what's it doing with these feathers then? This thing is not using them to fly. It's going to probably lose most of them over the course of its evolution. But it and Sinosauropteryx before have one thing in common, and it's that they're both small. They're both little dinosaurs, maybe like this big. And little animals have a hard time maintaining their body temperature. They lose a lot of heat to the environment because they're small. And one way that animals get around that problem is by growing, in mammals' case, hair, and in dinosaurs' case, feathers. So it's very likely that feathers that birds use to fly today first arose to help maintain their body temperature. And then they were progressively altered along the course of their evolutionary history. And we can see that when we look at the wings. So birds today have wings. They use them to fly, and we can kind of think of them in two different ways. So the wing is a flight surface, right? It catches the air and lets the bird soar, and that's what these long feathers are for here. And then the wing is also, at the same time, a modification of the arm, of an arm that's not too unlike the ones that we have ourselves. So let's first think about those feathers. So we've seen before that they're little short hair things. How do we get from those to a long wing feather? Well, we can see that transition happening. We can see things like Velociraptor here, the menace of Jurassic Park. If you zoom in on this region of its arm here, this is the arm bone right there, there's all these little pock marks. And what those are knobs where the quills of the wing feathers would have inserted into the arm. And so the feathers of Velociraptor would have been nearly identical to the feathers of an eagle or an owl. But Velociraptor isn't flying. It's small, so what's it doing with them? Who knows? We have some ideas, because other animals have these same kind of wings too. Things like Ornithomimus, which is a lot bigger than Velociraptor. So Ornithomimus stood probably at least as tall as a person or bigger. So it's about ostrich size. Ostriches aren't flying. Ornithomimus isn't flying, but it still has these huge wings. And the artist who drew this beautiful painting here gave us a clue as to what we think they might be doing. You'll notice that the artist colored this pretty garishly, bright blues and reds. And it's because we think that these dinosaurs were probably using their wings as big display structures, big billboards that they could flash to their neighbors and say, I'm a suitable mate. You want to have children with me and not Dan down the street. And birds today do the same thing. Birds of paradise use their wings and feathers as display structures when they're courting their mates. And so this is probably a very, very ancient behavior, going back millions of years to the age of dinosaurs, that is then replayed on BBC's Planet Earth for us to watch. Another potential thing that they're doing with these wings is incubating their eggs. So this is a dinosaur called Oviraptor that you find a ton of in the Gobi Desert of Mongolia. And you find them a lot on nests of these long oval-shaped eggs, and they're laying on top of them. And what these are mother oviraptors, or maybe father oviraptors, sitting on their nests. And if you look at the arm of the dinosaur here, you can just imagine those long wing feathers extending out and being in the perfect position to cover those eggs and protect them from blowing sand and debris and help to keep them warm and at the right temperature. So there's a couple of different things that these feathers could have been doing, completely unrelated to flight, but equally fulfilling an important job for these animals. Now the other thing you could think of as a wing is not just as a flight surface, but as an arm. So this is a picture of an eagle taking off. And if I was to lose 200 pounds, stick a bunch of cardboard feathers on my arms, and try to do the same thing, I still wouldn't be able to fly. I'd have the flight surface, but my arms wouldn't be able to do the job of the eagle's wing. And that's because bird arms are also highly modified. Birds can do one really powerful muscle contraction in their chest that swings the whole arm forward and then pulls it down. It's really efficient and it's really powerful, and they need that in order to fly. So that clearly has to have arisen for flight, right? Well, no. As the theme of the talk is no. This is an animal called Deinonychus, the real inspiration for the Velociraptor of Jurassic Park. And you can see it's a good-sized animal. And its arms function in the same way as the bird, the way that they're extended forward like this. They have forms of all of the same specializations that bird arms have that allow them to really quickly whip their arms forward and pull them back. Birds use that to fly. Deinonychus is probably using it to grab prey with its wicked hand claws and then bring them back to its feet and its head to do its job as a top predator of its environment. And Deinonychus, therefore, is probably a pretty good hugger, but you would not want to get hugged by Deinonychus. But it has all these same features that birds then co-opt into beating their wings through the air, something that initially appeared as a predatory feature of their ancestors. And just to highlight one of those adaptations, there's this wrist bone, the half-moon wrist bone, that birds have today that kind of lets their hands flick as they're doing their flight stroke. Deinonychus has that. All of the quote-unquote raptor dinosaurs have that. And they're all using it to do the same motion, but for a different purpose. And so let's turn to the air sacs. And I've kind of thrown a lot of information at you, so let's take a break. Let's take a breather. Everyone just... And that was kind of a waste of time, right? Every time we take a breath, we're kind of wasting time, because as mammals, we breathe in, get a bunch of fresh air, and then a bunch of dead air comes out. We're not doing anything with it. I'm doing something with it, I'm talking to you. But for the most part, it's kind of useless air. But birds don't have that problem. Their air sacs give them something that we call unidirectional airflow. What that means is that when they breathe in and when they breathe out, fresh air is hitting the lungs. So birds are never wasting a breath. This turns out to be really great for flying because it's kind of like an oxygen mask of like a fighter plane, right? It helps them be at high altitudes, and it helps them be very efficient. So they're not wasting a lot of energy with each breath as they're flying through the air. The other thing that air sacs do is they invade the bones, and this is important. So where are you going to put all of these sacs of air? Well, let's put some in the hips, and some in the backbone, and some in the shoulder. Wherever we can throw these things, we'll do it. They make the animal very light. So if you've ever held a really big bird, you were probably surprised at how light it was compared to maybe a dog of the same size. But because they invade the bones, we can actually see air sacs again in dinosaurs. And again in things that are not flying. So this is Majungasaurus. Stands about as tall as me at the hip. I'm wearing his skull on my lapel. And we've been able to map out the position of Majungasaurus' air sacs. And they match perfectly what you see in modern birds, based off of where they're invading the bones. And T-Rex puts this guy to shame in terms of having puny little arms. So it's clearly not flying. Other dinosaurs too have them, bigger things even. Things like Brontosaurus has these characteristic air pockets of the air sacs invading the body. And they're probably really beneficial for huge things like this because it helps them stay light. They can get a lot bigger than a mammal of the same size could be because they're lighter than you would really expect. And so these air sacs appear well before flight does in dinosaurs. And they're helping to do two things. They're helping to keep them light and keep them efficient. And while those are great things to do if you're flying, they're also just really great things to do if you want to be a successful animal in your environment. And so that's probably where air sacs are coming from. And that brings us to the last bird feature that I want to convince you of that did not arise for flight. Right? And that's the tail fan here. This is a rudder structure. So what does an animal that's walking around need a rudder for? Well, Deinonychus gives us another clue. So Deinonychus has a long tail, unlike a bird. But like a bird, the back part of the tail is stiff and rigid. It's held in place by tendons that have turned into bone. And the base of the tail is really flexible and can move around quite a bit. The same thing that's happening at a bird's tail fan that's rigid at the back and flexible at the base. Deinonychus is probably using this as a balancing structure. So just like a tightrope walker might have a beam as they're crossing, it's doing somewhat the same thing. It's helping them make sharp turns in their environment as they're pursuing their prey with their flight stroke grasp. And then this gets elaborated on as you get closer to birds even. So this is a little thing called Caudipteryx from China, and its tail is now starting to get short. And it's still rigid back here, still flexible at the base. And if we put some meat on these bones, you can see from the fossils and the fossils of its feathers that it has a tail fan, just like a modern bird does today. These feathers fan out from the back of the animal, and again, this is kind of a weird looking funky chicken. It's not flying. What's it doing with it? The colors are the clue once more. It's probably another display structure, another big billboard you can flash to say I'm healthy, I'm a good choice of mate, just like birds do today. So these four features that birds today use for flying first appeared in dinosaurs that were doing entirely different jobs. So how did birds come to have them? Well, let's return to the environment of the gibbon. Only, let's go back 90 million years, and it's a little less tropical, we'll say, but still a huge forest. I'm a little dinosaur, and I have all of these features that I've inherited from my ancestors: the feathers, the wings, the tail fan, the air sacs. And my job is to get around this environment. I have just padded my resume with a bunch of things that would be great if I maybe tried to fly around. And we have fossils of things that did that. So this is Microraptor, a little four-winged dinosaur that lived in China. And it's just one example of a lot of dinosaurs that have all of these features assembled and are maybe starting to experiment with flying around. Microraptor has the wings and it has the feathers, the tail fan too. And trust me, the air sacs are in there. You just can't see them. And so Microraptor illustrates that once you've assembled a suite of features, evolution can then act on them in new and unforeseen ways, right? Who would have thought, if you were 100 million years in the past, that the little fuzzy thing running around would someday use that fuzz to fly through the air? And this process of exaptation that we see in the fossil record isn't just exclusive to dinosaurs, it isn't exclusive to birds. It's the same process that can take a shoulder that initially appears to brachiate through the trees and make it something that's capable of throwing a spear or throwing a baseball. Because evolution isn't just the story of everything else on Earth. It's also our story. We are just as much a part of the history and tree of life as anything else on Earth. And so we are a part of this diversity of life. This diversity that when you look out and see, variation, selection, and inheritance, that structures the world into different jobs and makes animals better and better at doing those jobs over time. You can see the same things going on in all of these animals, producing variation. Things from fruit bats to chickens to humans. By changing the instructions, you can change the end result. And by looking at the fossil record, we can fill in the gaps of the family tree and really broaden our understanding of what evolution is, how it happens, and how it has led to everything we have on Earth today. So thank you very much for coming today.
All right, thank you very much for coming. Before we invite the speakers up for questions, I just want to advertise the next talk happening in Science and News, the Molecular Macarena, Coordinating Your Body's Movements, all about kind of the big stuff, how your body moves, develops, and that kind of thing. It should be really, really interesting. So why don't we invite our speakers back up, get a little question and answers. If you want to ask any other questions about details that might not have been covered in the talk or other science stuff that are just cool.